Okay, so following on from the previous lesson, our fourth step now is to determine which of the constants is positive and which is negative. Okay, so if it's going to be positive, it'll be written in the form of, since we have an x, a y, and a z, it'll be written in the form of a e to the square root of k squared plus l squared by x plus b e to the minus square root of k squared plus l squared x. Okay, so this would be, if the constant was positive, this would be our solution. If the constant was going to be negative, it's going to be something of the form c sine kx plus d cos kx. Okay, so now what we must do is we must take into account our boundary conditions, and we have to look and see what answer we're going to get by substituting for x equals to infinity and for x is equal to 0. And then we also do this for y is equal to 0, y is equal to a, and also for z. Okay, so let's see what happens when x goes to infinity. Okay, well, when x goes to infinity, what we can do is we can let our constant a is equal to 0. Okay, so we can go to 0, and we see for the b by e to the minus square root of kl squared plus l square root of k squared plus l squared to the x, this one will go to 0 as x goes to infinity. So far so good, we'll satisfy that. What about if our solution for x is going to be negative? Well, if the solution is going to be negative, as x goes to infinity, this will never go to infinity. So therefore, the potential will never go to 0. Also, if we look at what happens when x is equal to 0, for x is equal to 0, we will have a plus b, and we can see that we could have a potential for that. What about when x is equal to 0? Well, when x is equal to 0, we'll have the sine kx will go to 0, and we'll have some other function here. But what about the y and the z? So if y was positive, essentially our potential, we'd have to have a and b are going to have to be 0, which means you're going to have a potential is going to be 0 everywhere. If z is equal to 0, and if that was positive, it means that a and b, these constants, would have to equal 0. So therefore the potential is going to be 0 everywhere. So clearly that's not going to work. So the only thing that does work is x C1 is going to be positive, and C2 and C3 are negative. Okay, so let's just write that out. So what we have here is d2x equal to k squared plus l squared by x. We'll have d2y over dy2 will be equal to minus k squared by y, and d squared z all over dz squared will be equal to minus l squared z. Okay, so these are going to have the solutions of the form for x. It's going to be positive, so it'll be equal to a e to the square root of k squared plus l squared by x plus b e to minus square root of k squared plus l squared dx. For y, is going to be a negative solution. So we have C sine ky plus D cos ky, and for Z it's also going to have a negative solution, so it's going to be C sine Lz plus C, we're going to use E here, plus F cos Ly. Okay, so these are solutions. Now, just to go through it again, x must be positive, otherwise the potential is going to go to 0 everywhere if x was a negative. Okay.